Assalamualaikum and good day, dear students. Now, let's continue our discussion on chapter 2, bracketing methods by using bisection method. Bracketing methods. Let's discuss on the idea first. What is actually bracketing methods? So, let's look at this figure 4 here. Figure 4 illustrates the basic idea of bracketing method, that is guessing an interval containing the roots of a function. Starting point of the interval is a lower bound we denote as L, small l here. Endpoint of the interval is an upper bound we denote as u, as subscript u. By using bracketing methods, the interval will split into two subintervals, and the size of the interval is successively reduced to a smaller interval. The subintervals will reduce the range of the intervals until its distance is less than the desired accuracy of the solution. So let's look at this figure 4 here, graphical illustration of bracketing methods. So, bracketing methods always bracket your roots, always bracket our roots of the function. Means that by using bracketing methods, we will guarantee we find at least one solution or one root at the end of the computation process. Okay, first, to start using bracketing methods, okay, we must to have the lower limit and also upper limit, where the lower limit and upper limit always bracket your roots. Okay, always bracket your roots. How to know? Okay, is it you choose the correct lower and upper limit or not? It means that your FA multiplied with your FB must less than 0. Okay, then we can find one solution. So this is our aim. We want to reduce this interval of AB so that our interval become closer and closer to the true or to the roots of this function. Okay, so after you decide, okay, after you do the bracketing methods by using bisection or force position method later on, you will have two subinterval. Okay, you will have two subinterval, means that this is your SL, this is your SU. Then if this is your SR, then you will have two subinterval. This is your lower subinterval, this is your upper subinterval. Then we must to decide, is it our root, okay, is it our true solution lies in lower subinterval or upper subinterval. So we have the test, alright, and then from that test we can decide our new subinterval or new interval. Then we can reduce the interval so that that interval become closer and closer to the our roots. That is the idea of bracketing methods. So bracketing methods always converge to the true solution. Okay, that's why our starting lower and upper limit must guarantee that it brackets our roots. Okay, so there are two types of bracketing methods. The first one is bisection methods, and the second one is force position methods. So we will start with our first discussion. Okay, we will look at bisection methods. Bisection method is the simplest bracketing method. The lower value SL and the upper value SU, which bracket the root, are required. The procedure starts by finding the interval SL SU where the solution exists. Okay, means that the first thing, in order to use bisection methods, this point here. Okay, bisection methods required two starting values. Okay, two starting values, which is X lower and also X upper. Alright, next, the decision of X lower and X upper must bracket your roots. It means that, okay, it means that f X lower multiplied with f X upper must less than equal to 0. So if this satisfies, then we start our first iteration by using this value of your X here. Alright. Okay, continue. As shown in figure 5, at least one root exists in the interval of your lower and upper limit if this satisfies. Alright, so figure 5 shows you that two possible pattern or behavior of our graph. Okay, either the first one or the second one. Alright, the first graph, okay, if your graph is something like this, so you will have your SL here and then SU here. So SL give you FSL positive, okay, and then FSU negative. So if we multiply these two, we get negative. So means that this can be our lower and upper limit because it's guaranteed that we will meet one solution. Okay, alright. Or in other way around, your graph or your function may behave like this. Okay, where your lower limit give you FSL negative and then your upper limit give you FSU positive. So multiply these two also give you negative value. So it means that we can start our bisection method by using this SL and SU because these two S bracket our roots, because this interval guarantee that we will meet one solution. Okay, now we look at the algorithm in order to implement bisection method to calculate our roots for the given function fx. Okay, for the continuous equation of one variable fx equal to 0, step number 1, choose the lower guess SL and the upper guess SU that bracket the root such that the function has opposite sign over the interval x between SL and SU. Okay, let me give you the idea on this side here. Alright. Okay, let's say this is our function. Okay, then this is our true solution. Okay, this is our true solution here where your fx cross the x-axis. Okay, this is our true solution. So now we have to decide SL and SU. So we need to choose SL somewhere here Okay, so here is our FSL, which is give us positive value, and then we decide this as our SU. Okay, where we get here FSU is a negative value. So step number 1, okay, step number 1, we decide X between XL and XU, and we already checked that FXL multiplied with FXU less than 0. Okay, so this is satisfied. Alright, then step number 2, we start our first estimation. Okay, we calculate the estimation roots denoted by SR is computed by using this formula. So this is formula for bisection method. Okay, this is formula for bisection method. SR equal to SL plus SU over 2. Okay, so step number 2, okay, step number 2, we calculate SR equal to SL plus SU divided by 2. So let's say by using this bisection formula, we get here is our SR. Okay, this here is our SR. Okay, so now we have two interval. Okay, we have two interval. This is our lower interval, lower subinterval, and then this here is our upper subinterval. Now we need to decide, is it our roots, okay, lies in lower subinterval or upper subinterval. So we go to step number 3, use the following evaluations to identify the subinterval that the roots lies. Okay, so we just use only first test condition, which is we check for FSL multiplied with FSR. Either it gives us less than 0 or greater than 0 or equal to 0. If FSL multiplied with FSR negative value, then the root lies in the lower subinterval. Then set our new upper S equal to SR and repeat step number 2. However, if FSL multiply with our FSR positive value, then the root lies in the upper subinterval. Therefore, we need to set S lower with our new value, which is come from the SR, and repeat step number 2. But if FSL multiply with FSR equal to 0, then the root is equal to SR. Hence, we terminate the computation process. Okay, let's look at this here. So, let's check our interval. Which interval, okay, satisfied the condition? Step number 3. Okay, so from here, this is our SR, therefore this is our FSR, which is negative value. Alright, so then I test FSL multiply with FSR. Okay, so from this figure, my FSL is positive, then my FSR is negative. Okay, therefore this will give me less than 0. Hence, my XU must replace the value of XR. Okay, means that now my XU go towards the XR. So now this become my new XU. Okay, so now you can see now the interval become smaller and smaller. Okay, because we aim to this true solution here. All right. Okay, step number 4, calculate the approximate percent relative error by using this formula. Step number 5, compare with the stopping criterion. If epsilon A less than the given prescribed tolerance, then stop the computation. Otherwise, we need to repeat step number 2 by using the new interval. Okay, so we need to do the checking process here, and then after that, if not satisfied, we need to repeat again step number 2.